Yeah, good morning, good afternoon, good evening, everybody. I can see people are rolling in for what's going to be absolutely wonderful EMinar. So welcome to Wednesday's EMinar day. And we're very, very pleased today to have a presentation from Paolo Dell'Aversana on integrated electromagnetic methods supported by machine learning for risk mitigation in exploration sciences. Just very quickly, for those of you who may be new here, you can go on the MTNet webpage. You can see the link below, and here you'll see the link to see prior web EMinars, and these are on YouTube, and you can get the PowerPoint presentation, and you can register for upcoming EMinars. And just one note for all of you listening and watching, we still have 3 open spots in November, December, and we would really like to see someone put the name forward to give an EMinar to the international community. The work done by everybody is valuable, so please be willing to talk about it. So you are on a Zoom webinar, and you have these controls in a webinar. You can send a chat to the panelists. You can raise your hand if you want to speak at the end, and we encourage this. We encourage discussion. And then there's the Q&A, and we'd like you please to send all questions in the Q&A. You can send them on the fly, clarifying questions, and Paolo will look at these, and if it's a short clarifying one, he may answer it on the fly, or he may leave it to the end. Okay, a very quick advertisement for next week's EMinar, which by chance is on the same theme, machine learning based geoscience, and this is from Michael Perch, also known as the Geostats guy, and you can look him up on Twitter or on GitHub. He gives out an awful lot of Python codes for free, and so that'll be, unfortunately, because of Michael's teaching commitments, it'll be quite late, one in the morning on Thursday morning, actually. So people in Europe will have to stay up late if they want to watch this live. And for those of us in the Americas, it's going to be late afternoon, early evening. And in Asia, it'll be early morning. So for today, as I say, we have the presentation by Paolo on integrated electromagnetic methods supported by machine learning for risk mitigation. You'll all have read Paolo's CV. He comes from geology and a physics background, which is wonderful. 35 years of experience in geology and geophysics, 27 of those in the hydrocarbon. Since 2002, so for 20 years now, Paolo's been a senior geophysicist at SPA, expert in integrated methods and data science, author of several patents, published more than 100 papers and 5 books, and has received any award of best technological innovation of the year. And Paolo was a finalist in the Abu Dhabi International Petroleum Exhibition for the Breakthrough Research of the Year. So I'm going to stop sharing now and hand over to Paolo.
Thank you very much, Alan, for your introduction. And thank you everybody for attending this webinar. I share my screen and my presentation. I hope you can see it right now.
Yeah, that's perfect.
Good. So I'm pleased to give my contribution to this EMinar series from the point of view of energy industry. And so today I'm going to talk about integrated electromagnetic methods supported by machine learning for risk mitigation in exploration geosciences. Let me start from the end. This is just a summary slide of my talk. It is very important because it summarizes the main results of the case history that I'm going to discuss today. And on the right panel, you can see a oil prediction map, probabilistic prediction map. Colors in red, we have high probability to find oil at reservoir depth, whereas in blue we have 0 probability to find oil. And the important thing is that this map was created by myself and my team about 10 years ago. And we used the seismic data, electromagnetic data, gravity data, calibrated by well logs, and machine learning algorithms. And the good news is that several years later, after producing this map, we drilled several different wells in the same area, and these wells fully confirmed our probabilistic map. So this result is very important because it represents a real case of probabilistic prediction based on EM combined with the seismic and gravity. Prediction of oil distribution in a wide and complex exploration area. And in particular, these two wells that are very important here. This is an appraisal well that we drilled in 2019, and it was an oil discovery. And it is in the red part of the map, so where we predicted very high probability to find oil. Instead, the well that we have drilled in the bottom part of the map, slightly outside the map itself, was an exploration well that we drilled about 6 years later, the map. And it was a dry well, unfortunately. And indeed, it is in the low probability area to find oil. And so these two wells are fully consistent with our map that we published in 2012 for the first time. So you can find this map for the first time in first break in 2012. So 7 or 8 years before drilling the wells. And this our map is very important because it is the normalized electric and magnetic response in the same area. And I projected the wells on this map, and you can see that the oil discovery in the upper part of the map falls in the high electromagnetic response of the map, whereas the dry well is located in the low electromagnetic response. So this is again a fantastic prediction many years before drilling the wells. So this is just the end of the story. Now let's see how we obtained these maps step by step. So I'm going through the entire workflow that allowed us to create these probabilistic maps many years before drilling the wells. So this is the geophysical problem that we have had in the exploration area. It was an area in the Barents Sea, offshore Norway. We wanted to define the lateral extension of hydrocarbon distribution in 2 stacked sand reservoirs in a complex geological setting with many faults, and there was also a carbonate platform below the reservoirs, complicating the electromagnetic response. So it was a very difficult interpretation problem from an electromagnetic point of view. And this is the scheme of our approach, summarizing the entire workflow. So we used the seismic data, electromagnetic data, so control of the source electromagnetic data, and also gravity data. And we used the wells and borehole information for calibrating our data at well location, because at that time we already had 3 exploration wells already drilled in the same area. And from this data, we went through a complex integration workflow, trying to combine the seismic, the electromagnetic, and the gravity response into resistivity, seismic velocity, and density models. After this process, we calibrated both data and models at well location in order to create a very robust training data set for training a deep neural network and other machine learning algorithms, with the final purpose to predict far away from the wells the probability to have oil or gas or brine far away from the wells. So this is the workflow, and I will give you an overview step by step of this workflow. Just a few words about the location of the reservoir area. So in colors here, we have a Permian carbonate platform running below the reservoir area. It is a depth map of the carbonate platform that was retrieved from pre-static migration of seismic data. And this is just the depth map of the upper reservoir, and this is the depth map of the lower reservoir. This is the same map of the lower reservoir co-rendered with the carbonate platform that is represented by these contour lines in this general map. This is just to give you an idea of the complexity of the problem. Here you can see a very big fault of the carbonate platform, and also very big faults in the reservoir area here. And this is the area where we acquired controlled source electromagnetic data. These are just examples of towing lines of CSEM data. And the symbols represent the controlled source EM stations. We collected about 110 EM stations with two central frequencies of 0.15 Hertz and 0.5 Hertz, plus all the harmonics, of course. And also we have gravity data in the area. So on the left panel here, you can see a map of the first vertical derivative of the Bouguer anomaly that is co-rendered with the carbonate platform here. And here you have an example of a seismic line extracted from the seismic volume that is represented in the upper right panel here. You can see the top reservoir and the bottom, the lower reservoir here, and also the carbonate, the top of the carbonates. And here you can see this big fault, and that is exactly this fault here that you can see also on the map. So you can see also many faults in that cross the two reservoirs. So it is a very complex situation from a structural and geological point of view. And again, here you can see the co-rendering between the Bouguer anomaly and the carbonate platform. And this is the first vertical derivative of the Bouguer anomaly. It is a high-pass filter of the Bouguer anomaly that is very important for our purposes. And this is a basin where you can see a minimum of the Bouguer anomaly. So we went through the integration workflow for combining this big amount of multi-physics data, and we started by modeling CSEM data, so electromagnetic data, using the constraints from seismic data. So the first step of our workflow was to import interpreted seismic horizons from the 3D and the 2D seismic volumes in order to have a geometrical model in the electromagnetic domain. And we created these layers using seismic information, and then we filled these layers using resistivity values from the well logs estimated from the well logs. And then we ran an iterative 3D forward modeling trying to fit the electromagnetic data in order to create some type of initial resistivity, 3D resistivity model in the area, in the same area where we have the seismic data. And just to give you an example, this is one line crossing the area of interest, and these symbols represent the stations, the CSEM stations. And here you have an example of seismic layers imported in the electromagnetic domain, populated with resistivities coming from the wells, and section by section we created a 3D, an initial 3D resistivity model, something like that. This is just a preliminary 2D section extracted from the 3D volume in terms of resistivity, calibrated at well location. And this model was very useful for triggering an optimized inversion of CSEM data for each line, for each one of the electromagnetic lines, in order to refine our resistivity model. This is just a set of examples where we fit the observed response, the electromagnetic response, the magnitude versus offset electric response. So this is the blue line, that is the model response, and the red squares represent the observed CSEM data. And you can see that the fit is pretty good just by trial and error forward modeling. And then we ran optimized inversion for each one of the CSEM sections using our starting model. And this is an example along the same line of resistivity model. So in red, we have high resistivity representing the reservoirs filled by oil. And also we have the carbonate platform here in yellow. It is quite resistive here. This resistivity is about 30-40 meters. And in red, we have more than 50 or up to 100 ohm meters. And then we used also gravity data. So using the same seismic constraints, we modeled also the Bouguer anomaly and its filters, high pass filters, trying to fit the anomaly and to retrieve a density model for each section consistently with both seismic and electromagnetic models. So geometries comes mainly from seismic, but they were slightly modified, taking into account the Bouguer anomaly. So here you are looking at a combination of gravity information with seismic information that is absolutely consistent with the CSEM resistivity model. So at this point, we are able to see a combination of electromagnetic, gravity, and seismic response at the same time for this specific section. We applied the same identical workflow for each section. They were 11 sections where we have all this type of seismic, gravity, and electromagnetic information. This is another example, another line, again, CSEM line, where we have also the Bouguer anomaly. And this is the seismic line where from which we extracted depth, the depth of our reservoirs, the top reservoir, the bottom reservoir, and the carbonates. And this is an example of a modeling of CSEM data in the electromagnetic domain. And this is the final optimized 2D inversion. And this is the modeling of the first vertical derivative of the Bouguer anomaly. So basically, we applied the same procedure for each line, and we were able to get seismic velocity model for each section, density model for each section, and resistivity models for each section. Of course, we have also the electromagnetic responses measured at sea floor for many frequencies at many offsets. So using all this information in both model and data space, we were able to create a big multiphysics feature matrix, including all these observations and models, parameters, multiphysics models parameters. And this multiphysics matrix was used as an input for machine learning, for a very complex machine learning workflow. Because, as I told you at the beginning of my presentation, our objective was to create multiphysics models from multiphysics data and to calibrate these models and data at well location, and then to expand this information far away from the wells in order to predict from a probabilistic point of view the presence of oil or brine far away from the wells. And this was done using the machine learning approach. So the first step of our machine learning approach was to populate this big multiphysics feature matrix that represent the input of our machine learning workflow. So the features that we used are, as I told you, in both data space and in the model space. So the features in the data space that we used for creating our training data set are given by 2-way times at target depth, then the CSCM response in terms of EM amplitude and phase at many frequencies and many offsets, plus additional attributes derived from electromagnetic response, such as the symmetry attribute. It is a very interesting attributes that represent the symmetry between the in-towing and the out-towing response on the CSCM data. It is very important for detecting resistivity boundaries from CSCM responses. Finally, we used also gravity attributes in terms of Bouguer and special filters and derivatives of Bouguer anomaly. Then we included in the same multiphysics matrix also model space information, such as interpreted horizons from seismic in depth, the resistivity models that we retrieved from CSCM optimized inversion, and the density models that I showed you before for each line retrieved from gravity model. This is just an example of normalized features along one lines. So on the horizontal axis, we have the sequential numbers of CSCM receivers for this specific line. And these are the trends of several attributes for these lines. You have to imagine that for each line, we have all these attributes that we used for populating our training data sets, because we calibrated these attributes at well locations. And the first step of every machine learning process is features engineering. So we need to rank the importance of the different attributes, the different features, for distinguishing between oil from water, from brine. And here we used the different indicators, such as the information gain, the gain ratio, Gini index. Each one of these indexes basically says how much important is each individual attribute for distinguishing oil from brine, where we have the calibration of the wells. So we can use the wells for calibrating our features and for understanding their ranking in terms of diagnostic power. And also we used many different methods, many different machine learning methods, not only deep neural networks, but also decision trees, random forest, naive Bayes, CN2 rule inducer, and adaptive boosting. And we applied in parallel all these methods using the same inputs, the same data, in order to classify and to distinguish brain from oil far away from the wells. And here we have a sort of a classification, a sort of ranking of our machine learning classifiers using these indicators. The most important is precision. Basically, higher is this precision, higher is the reliability of the classifier. And we can see that this classifier have quite high indicators when we test them on the training data set. And just examples of statistical distributions on the training data set. When I say the training data set, I mean that we are using a labeled data set. So we are using the data that are calibrated at well location. So we use data and models parameters calibrated at well locations in order to see, to verify the diagnostic power of each one of these attributes. So on the vertical axis of these graphs, we can see the probability density distribution for a specific attributes. For instance, here you can see the normalized amplitude of the electromagnetic field at an offset of 6-7 kilometers at a frequency of 0.5 Hz. This is a very important attribute that is very, very strong for distinguishing brine from oil. And in fact, you can see that the normalized probability density distribution is very different for brine and for oil. It means that we can use this attribute for separating the two cases of brine and of oil. Also, the symmetry attribute at 5 kilometers is pretty good, but not so good as the previous attribute. And we have many attributes. For instance, the normalized resistivity of the upper reservoir that was retrieved from optimized inversion of CSM data is very important for separating brine from oil. However, resistivity is not necessarily a good oil indicator. In fact, for the lower reservoir, you can see that the two distributions are quite overlapped. This is because the lower reservoir was quite close to the carbonate platform. And so resistivity, in that case, didn't represent a very good indicator for distinguishing brine from oil. Different story was for the upper reservoir that was quite far from the carbonate platform. And so on. We made the same analysis for many attributes. And the end of the story is that we, of course, must use all of them, not just one or two. If we use just one or two or three attributes, so we can fail in the distinguishing brine from oil far away from the wells. Instead, if we use 15 or 20 attributes in the same machine learning process, we have a good chance for separating the case of brine from the case of oil far away from the calibration points. And so it is exactly what we did. We trained our 6 algorithms simultaneously, including deep neural networks, and we tried to create maps of predicted brine and predicted oil far away from the wells. So creating maps like this, where the colors represent the oil probability, basically. This is just an example for one line. And so in colors, we can see the probability to have oil just for this line, or a single line. In red, we have high probability, and in blue, we have a low probability. We did the same for all the lines. and then we interpolated the results for all the lines, and the final result is this one. This is just one of the maps that we created. Purple means high probability to have oil in the area, and this is the appraisal well that I showed you at the beginning of my talk, where we effectively found an oil discovery. This is another map, again, with the same result, basically with different colors, but with the same results. And this is the map that I showed you at the beginning of the talk. And this is the paper that we published in 2012, where you can find all these maps, and you can find also the procedure and the workflow, at least part of the workflow that we used for creating these maps and for predicting the results of the wells that we drilled several years later. Again, this is the first slide that I showed you in my talk. So this is the oil discovery, whereas this is the dry well. Unfortunately, this was dry, and it is fully consistent with the low probability values that we have in our probabilistic map. And this is for the lower reservoir. So we did the same. We applied the same procedure for the two stacked reservoirs. The previous map was for the upper reservoir, and this is the similar map for the lower reservoir with similar results, basically. And these are the maps, or the two maps, the two maps that you can find exactly like you are looking at in this slide in my paper published in 2012. So in conclusions, all the maps that we produced and published over the years show very high probability to find oil in the western sector of the exploration of the explored area, in full agreement with the appraisal well that we drilled in 2019, 7 years later, and also are in agreement with the dry well that we drilled some years later. And the conclusion of all the conclusions is that the right way to proceed in very complex exploration areas like this is trying to integrate everything that you have. So sometimes electromagnetic data alone can be misleading, especially if you have carbonate platforms or other resistive layers in the area. They can confuse the interpretation. But when you use also seismic data and possibly gravity data, if you have, with the support of machine learning, you can improve a lot the reliability of your interpretation. And I think that this was my last slide, and I will be pleased to answer to your questions, comments, and so on. Thank you very much for your attention.
Well, thank you, Paolo. That was absolutely wonderful. A clear demonstration of the need for multiphysics. Just one question for me while people start rolling in with their questions. Why was that well drilled to the south? Because all of your predictors say that it was going to be dry.
Yes, the main reason is that at that location we had a very good seismic amplitude anomaly, and so people was addressed by that seismic anomaly to drill the well, despite the low response of EM data. But you know that especially in hydrocarbon industry, in general, the background is in seismic, not in EM, and so people have more confidence in seismic than EM. And there was a good seismic anomaly. It was not in contradiction with the low EM response, because you know that when you have low gas saturation, and that was the case, you can have good seismic anomaly in terms of amplitude, but low resistivity, EM anomaly at the same time. And that was the case. And so that was the reason, basically, because they drilled at that location. Unfortunately, the well was dry.
Brilliant. I'm sure that Max will want to jump in, but perhaps, Max, before you do, let's just get a question from the Q&A. Williams Lima. I'll read the questions out, Paolo, so they get into the record.
Yeah.
Williams Lima asks a couple of questions. Number one, is ranking of features equivalent / similar to a sensitivity analysis? And number two, related to the previous question, can uncertainty analysis of the inverted models be transferred to the ML classification probability estimates? If so, then the dependence of the probabilities on the uncertainties in the models could give some measure of the robustness and or sensitivity of the ML estimates with respect to the features selected.
Let's start from the first question. Yes, when we do a ranking of the attributes of the features, basically it represents a sensitivity analysis of the features with respect to the problem that we want to solve. In that case, we had the problem of classification. We wanted to classify brine and oil responses. And yes, the answer is that ranking the features represent a sensitivity analysis on the labeled data set, so on the training data set, for ranking, for understanding the diagnostic power of the different features. Regarding the second question, yes, when we run inversion using different types of algorithms, and we try to use both deterministic and probabilistic approaches. And when we run probabilistic stochastic approaches, we always get some type of model uncertainties. So not only the model parameters distribution, but also the model uncertainties. And that model uncertainties is introduced in the multiphysics metrics that we use for machine learning. And this uncertainty is propagated in terms of uncertainty on the probabilistic predictions.
Yeah, thank you, Paolo. There isn't another open question. Max, do you want to jump in?
Yeah, sure. I mean, one question I was wondering is, I mean, when you design your neural networks, for example, you have a lot of freedom, yes, how you do this. So do you have some general ideas, especially because you have these like very different properties, right? Also with different numerical ranges. So I suspect there are some normalization and so on. So can you give some insight into sort of you know, what are some good steps there, or some starting points for somebody who thinks, oh, I want to do something similar?
The first part of the job is to normalize the features in order to take all the features more or less in the same range, because in general, these features have very different values. So you are right, you are perfectly right when you talk about normalization. This is the first part of the job. The second part of the job is to use the labeled data set or the training data set for understanding how to set the hyperparameters of the neural networks and of the other algorithms. Indeed, for instance, when we use deep neural networks, we have a lot of hyperparameters, such as the number of hidden layers, number of neurons, the smoothing factors, the regularization factor of the network, and many parameters. And the only way that we can have for setting, for optimizing these parameters is to make a lot of trials using the labeled data set and to go through cross-validation test. Cross-validation test means that we apply the network and the other classifiers on the labeled data set, and we quantify their performance at each run. And in doing that, we are able to understand what are the optimal parameters for each classifier, including the network.
Okay, so I suppose you are, if you want to, at the same level as I am with this, in the sense that, okay, you try different things and you look at what works, but there, I mean, I find this is maybe one of the main difficulties in machine learning when you start.
Yeah,
that it's very difficult to know, okay, what is going to work and what is not going to work. Yes, and you look at the literature and you see these, you know, different architectures, for example, of neural networks. And certainly for me, I'm still a bit always puzzled. Okay, which of those should I try first? And, you know, that's I find still a very difficult
I agree with you. Yes, we also can see can look at the loss function, the trend of both loss and the validation, the training and validation loss functions. If the trend is a smooth decreasing trend, it means that your process is going well. If you see a lot of jumps in the loss function, it means that something is working not properly. So yes, there are several strategies that we can use for that. Then the experience, of course, plays a very important role in this process.
Yeah, Brian, one more question for me, Paolo, just so I fully understand. So your 3D model was forward trial and error, but all the work you've done now has been on profile. So it's been 2D inversions.
Yes. We basically went through 2D optimized CSCM inversion, and including joint inversion of magnetic and electric data, and 2D and 3D forward modeling of gravity data. Okay. Yes.
Okay.
That's true.
Yeah. Okay. Is there any more questions from the audience for Paolo? And I doesn't look like it. Well, I'd like to thank you very much, Paolo, for this really illuminating presentation, and it's wonderful. And thank you for giving us an EMinar.
Thank you very much. Thank you everybody for attending, and thanks.
So Paolo has given me already his PDF of his talk, so that will be up on the website shortly, and the recording of this webinar will be up when I get it from Zoom. So hopefully see everybody next week, and bye for now. Have a great week.
Thank you.
Bye-bye.
Bye.